Okay, good morning, all of you. Today we'll see the fluid properties. The first property we'll see, already we have seen so many properties till the time, density, bulk modulus, and other properties we'll talk about now. That is one is the most important property, that is the viscosity. So viscosity is such a property, whenever the fluid is in motion, then this property will comes into the picture. But density will be always remain, pressure will be always remain, whether the fluid is static condition or in motion. But now we are going to discuss in such a property which is only comes into the picture when the fluid is in motion condition. And what is the nature of this property? Everything we'll see one by one. So directly we are going to the slide and we'll see the properties, how this property is looks like. So already we have told about the fluid is in motion, then only the viscosity property is working. So just so here, before going to the viscosity property, just let you think in the fluid, what does it mean by the fluid? Fluid is actually the definition we have already seen. If you give some shear force, so it will undergoes for the continuous deformation when the fluid is in motion. The fluid definition, we are getting it. If you give some the shear force, however the small it is, so then the fluid undergoes for the continuous deformation. It undergoes continuous deformation. So if some fluid is coming, let you consider some fluid is coming, let it be gas or liquid, whatever it is, some fluid is coming with some velocity. And this velocity is the uniform in nature. Uniform velocity, the definition, we'll see the kinematics of the fluid chapter. But let you see some fluid is coming with the same velocity. All points having the same. If you goes the time to time, it is the each space you are considering at any instant of the time, let you take the now. If you consider each and every place having the same velocity, so it is known as the uniform velocity. So some fluid is coming with the uniform velocity. Let you take it as a liquid or gas, anything. Liquid or gas. Hence, here it is a flat plate is there. On presence of the flat plate. So what will happen? So fluid molecules will come and strike over the plate. So fluid molecules will comes, so it will comes and strike over the plate. And it got absorbed. So first thing happened, the fluid molecules strikes over the plate, and gets adsorbed. It is not absorbed. Absorb is a chemical process, absorption. It is an adsorption, mechanical process. It got adsorbed. Now then, what will happen? These molecules initially having some momentum because of its mass and velocity. So it will transfer its momentum with the plate. So second thing is the momentum transfer. So these molecules transfer its momentum with the wall and it got slowed down. Momentum transfer occur and it gets slow. We are talking about one molecule. 2-3 molecules you can consider also, more than one single molecules you can consider. So these molecules all are interacting with the plate, molecular momentum transfer occurring, and it gets slowed down. Then what will happen? After it getting the slowdown, and it try to be ejected from the surface. These molecules, after getting slowed down, it try to eject it from the surface. It is going out from the surface. It is try to be ejected from the surface. Flat surface. In the meantime, other molecules will come. So many other molecules will come. And whenever it is going out, so there it creates some collision. Collision will take place. Because other molecules are coming, it is going to be out. So hence you take some other molecules are coming here. So some other molecules are coming here and the collision is taking place. So it will cause some collision. Collision will take place. So in between two molecules also the momentum transfer will be happening. So whenever these molecules initially it's going to be eject, other molecules will come and cause the collision. Now the infinite number of molecules will come and it causes the infinite number of collisions. So how many number of collision it will happen? Infinite number of collision will be. We don't know whether the collision is elastic collision or inelastic collision. We don't going so far. So number of collisions will be happening. And due to the number of collision, the huge number of momentum exchange will be takes place. So due to this, the momentum exchange will take place. And what will happen? As the momentum exchange will be takes place, so these molecules, the molecules will comes in these molecules which is adjacent to the plate. Those molecules I'm taking. The molecule near the flat plate, just adjacent to the flat plate, will come in thermodynamic equilibrium. Will come in thermodynamic equilibrium. So due to the infinite number of collision, the momentum exchange will be happens in between the molecules and the flat plate continuously. And what is the consequence of it? The consequence will, the molecules adjacent to the flat plate will comes in thermodynamic equilibrium with the flat plate. So from that we can conclude. So the molecules adjacent to the flat plate will get the same velocity of flat plate. So no relative motion between the adjacent molecules and flat plate. So it will cause for the, in technically we are writing zero relative, very, very important thing we are talking about now, zero relative velocity between adjacent molecules and flat plate. This specific if you are talking about zero relative tangential velocity. More specifically, your tangential velocity. So zero relative tangential velocity between adjacent molecules and flat plate. What does it mean? Those molecules is nearby to the flat plate, having the same velocity of the flat plate velocity. That means if the flat plate is stationary, if the flat plate velocity is zero, so adjacent molecule velocity also zero. Both are stationary. If flat plate is moving with some velocity, the adjacent molecules will also moving with the same velocity. This condition, the most important condition, is known as the no-slip boundary condition. So this condition is known as the no-slip boundary condition. So whatever the flat plate velocity, the same velocity of the adjacent molecules. It is nothing but a conceptual paradigm, a philosophy we are talking about it. A concept. If the so it is due to the infinite number of collisions it is taking place. Due to the infinite number of collisions, the consequence is that the molecules comes under the thermodynamic equilibrium with the plate. If the collision is the perfectly elastic, there might be some normal component. If the molecules is the perfect collision, perfect elastic collision. So as there is a collision, there may be perfect elastic collision or some elastic collision. Then the molecule might have some normal component. But the tangential relative velocity will be zero. Tangential component, the same of the flat plate, but it might have some normal component. So that's why I'm telling zero relative tangential velocity between adjacent molecules and flat plate. This is called the no-slip boundary condition. So is it a ritual? Always it should be happen? No, it is not a ritual. So there is so many examples. There may be the violation of the no-slip boundary conditions. So no-slip boundary condition may be violated in several cases. So this case we can talking about. So what are the cases? First is if the rarefied gas molecules are there. So rarefied means the in between in a gas, if the two molecules attraction force is very less. So that is the rarefied gas molecules. In that case, what will happen? In that case, less number of collision will be happen. In that case, less number of collision will be. And due to the less number of collision, so the molecules adjacent to the plate will not come under thermodynamic equilibrium with the flat plate or plate. That is why here some violation of the no-slip may be happen. That means whatever the flat plate and the adjacent molecules might have some tangential velocity. Slip is there. That kind of flow is known as the slip flow. So no-slip, the deviation from the no-slip boundary condition that times up because the rarefied. So number of collision will be reduced. As the number of collision will be reduced, momentum transfer will be also, momentum exchange will also reduce. That will cause for the, so the adjacent molecules cannot come under thermodynamic equilibrium with the flat plate. It cannot establish this thing. Such a condition, there might have some slip flow will be taking place. There is another analogy, another theory regarding the no-slip boundary condition. That means this is a smooth plate we are considering. This plate is a very smooth plate. But smoothness is different. If you see the plate, the smooth flat plate, flat surface with some powerful lens, you can see there might have some undulation in this. The surface is not perfectly smooth, might have some undulation. So another theory regarding this thing is telling that the fluid molecules which is coming here, the fluid molecules which is coming, So how it will becomes the fluid molecules is just in this way. Adjacent fluid molecules will be like in this way. Light. This is the first layer, just adjacent layer of the plate. The above the layer having some velocity. Next layer having some more velocity. So layer to layer, the velocity is changing. Is taking place. So just adjacent layer having no velocity. Next layer having slight more velocity. Next layer further more velocity. So in such a way, the velocity is increasing. Layer to layer. So layer to layer velocity is increasing means the momentum also transferred in this way. So momentum transfer. So whether you go the normal direction, you will get much more momentum. And after going a certain distance, you can get the same momentum which was initially before the plate, upstream to the plate, after reaching the certain distance. So this thing we will see the boundary layer theory in the chapter, but just I'm telling, I've give you the insight of this phenomenon that as the surface is not smooth enough, so some molecules will be trapped in this way. So that may be the cause of the no-slip boundary condition. So if you could be able to give some high shear stress, high rate of shear, if you could be able to give, then we can create the motion of these molecules, first layer molecules, if you give the high rate of shear. So next thing is if you give high shear strain rate, then it is possible for violating the no-slip condition. Next thing, some induced thing. That means here, some temperature gradient if you create. So here in this side, some higher temperature, in this side, some lower temperature. So here the TH, here T. As you're creating the temperature gradient, so due to the gradient, all molecules will flow because of the density difference. So that time also no-slip boundary condition may be violated. So just adjacent. So you create one gradient. So because of this gradient, this molecules is getting some velocity, tangential velocity also. This is the phoretic motion. This kind of the motion is called the phoretic motion because of some gradient. So if the gradient is due to the temperature, thermophoresis. If it is due to the concentration changes, that is known as the diffusion forces. This way we can say it here. So thermophoresis, diffusion forces, if you create some temperature gradient or density gradient, you can violate the no-slip condition. Next thing is the very smooth tube, carbon nanotube. It's such a very fine surface finish is there in this tube. Because of this fine surface finishes, what will happen? The van der Waals force between the fluid molecules which is adjacent to the plate and the plate. So solid surface and the fluid, the van der Waals force is much more weaker than the order hydrogen bond of the water. So no-slip boundary condition may be violated. That means the attraction force here, if you consider the surface, so the attraction force between the surface and the molecules is much more weaker than the two molecules. These two molecules, if it is the water having the strong hydrogen bond, and this molecules and this surface is having the van der Waals force. If the hydrogen bond is stronger than the van der Waals force of bonding, then it can overcome. The molecules can overcome this van der Waals force and it can move. So nearby molecules also can bounce. Just adjacent molecules also can bounce. So carbon nanotube, one more example. I'm not going that much details, just give you that it is not an ritual. No slip boundary condition may be violated in different cases of the fluid. One prejudice is there, the rough surface, if the surface is a rough surface, it can also reduce the frictional resistance. That means if the surface, if you're considering the surface here, if the surface is not smooth enough, too much roughness is there in the surface. If you with this powerful microscope, if you see if the surface is very rough surface, in such case of the surface also gives some less frictional resistance. It is the just we are contradicting the prejudice. Always we know the smooth surface is the good surface and friction resistance is the less. But sometimes the rough surface also gives you less friction resistance. How it is? This consideration will getting here because of the roughness. What will be happening? Just I give you the idea here. So the adjacent fluid, if it is now some liquid is coming, let you consider some liquid is coming. So nearby to the surface, the liquid is converted into the vapor. So as it is becomes vapor nearby the rough surface, so the collision, less number of collision will take place, no slip condition might be violated. So in this case, the rough surface nearby to the surface due to the vaporization, so it having some slight velocity, slight tangential velocity, relative tangential velocity. So no slip boundary condition may be violated. If you extrapolate this thing, if you extrapolate, you will get some here. In this way, you can get it. I'm not going details. This is what is the velocity at that plate. So what I'm telling here, if it is a rough plate, so it will looks like in this velocity diagram. So here also some velocity is there. Layer to layer, the velocity is increasing. You can see from one layer to other layer. If you go in this direction, normal to the plate, you see the velocity is increasing. But at y is equal to, let you take the y direction here. So y is equal to 0. There is also some velocity, some amount of velocity. This velocity is called the slip velocity. You can find it out, this velocity also. How you will find it out? You have to extrapolate this thing in this direction. And this length, if you are getting ls, so US value will come ls into the slope you have to find out. What is the slope? So the slope is du dy at y is equal to 0. If you get the slope, you will get this in this way. This is a mathematical foundation I am showing you. The main reason is that because of the roughness, the nearby liquid molecules will convert it into the vapor. As it is converted into the vapor, the resistance will reduce. That's why the friction resistance will be reduced here. Now the concept of the viscosity, we'll see. Viscosity is the property which comes into the picture when the fluid is always motion. Because the fluid is at static condition, you see the fluid is at static condition, so no shear stress. Fluid at rest, there no shear component will be there. No shear component. And viscosity is causing due to the shear force only, not because of the normal force. So fluid is at rest, though the fluid having the viscosity, but it will not come any consideration. So viscosity is such a property which will comes into the picture when the fluid is at motion. fluid is at motion means there is some shear component must be there. Some shear component must be there because though it is very small quantity, but there must be some shear stress. And because of this shear stress, the fluid is undergoes for the continuous deformation. As the fluid is undergoes through the continuous deformation, then only the viscosity will come into the picture. So viscosity, the better to say, it is nothing but like a messenger. It collects some information from somewhere and it is convey the information one layer to other layer. How it looks like in the same example here, if you consider the fluid, we are telling about the no slip boundary condition because most of the cases the no slip boundary condition will be applied. So here the molecules is getting the same velocity of the plate. So what will be happen? Here the molecule having no velocity. Here the molecules having no velocity. So we are plotting here now. Along the y direction, we are plotting. So at the end, here is no velocity. If you go the above layer, it's having some slight velocity. So one layer to other layer having some differential velocity. So differential momentum. Next layer having slight more velocity. Next layer having some further more velocity. So in this way, if you go along y direction, you can be able to see the velocity is increasing up to a certain thickness. The velocity is increasing up to a certain thickness. So in this layer having some velocity, further layer slight more. In this way, one layer to other layer, the velocity is increasing in this way. After reaching some distance, it will get the 99% of the previous velocity. So if the previous velocity is the u infinity, so after getting a some level, it is getting that 99% of the previous velocity it is getting after going a certain distance. That is known as delta. We are telling about the boundary layer thickness. It is telling if you go y is equal to delta, you will get the velocity that is the 99% of the initial velocity, upstream velocity before coming to the plate. So that is the velocity distribution layer to layer. So if you join this line, this is known as the velocity profile. This is known as the velocity. So what the viscosity's role here? One layer to other layer, here because of the plates, some momentum disturbance is created. Here because of the plates, some momentum disturbance has been created. This momentum disturbance is conveyed. It is telling there is a disturbance of momentum. It tells to the next layer. Next layer tells to the next, further next. So one by layer, the message is going. The disturbance message is going. By the property, the name is the viscosity. Viscosity is a messenger for momentum disturbance. It conveys the message, this property. Say there is a plate. At a certain distance, there is a plate. If you go beyond y greater than delta, the velocity is near to very close to the previous velocity. So whatever the molecules at here, it cannot get the fill. It cannot fill the presence of the plate. So, but if a molecule is in here, it can fill the presence of the plate. So it's a boundary. There is a boundary. So if y is less than delta, the molecules can feel the presence of the plate because momentum is getting disturbed. Previously, momentum, whatever the momentum it was, here the momentum disturbed. If y is greater than delta, the momentum is not disturbed. So it creates one boundary. So y is equal to delta, it creates some boundary. And this is the nothing but the boundary layer. Delta is known as the boundary layer thickness. So the flow here, y less than delta, the viscous effect, the flow is the viscous. Viscous effect we can feel due to the viscosity. The viscosity property is telling one to other layer there is the presence of the plate. That's why the momentum changes is taking place. Beyond it, the molecules having viscosity, but it cannot tell. So there the flow is potential flow. What is the potential flow? We'll tell it later. In viscous flow, you can tell it later. It is not disturbed due to the presence of the plate. It may be disturbed by other factors, but due to the presence of the plate, this is not getting disturbed. And it sets there is a demarcation. There is a demarcation between these two layers, upper of the layer and lower portion of the layer. So viscosity is such a property. The definition was the viscosity, but we have to tell. Viscosity is a property which tells about the momentum changes. It is a messenger for momentum disturbance. If there is some momentum disturbance, it will tell to the one layer to the other layer. There is somewhere there is a momentum disturbance. So that is the case here. So viscosity, whenever we are talking about the viscosity, we have to tell one layer to other layer. Just you consider. So let you take some places we are taking here, one box. Let you take here in this shown, whatever the molecules are there. Yeah. It's having some velocity. And the upper layer here, whatever the velocity molecules are there, it having some more velocity. So as upper layer having some more velocity, it tries to drag this lower layer molecules in this. It tries to drag the lower layer. And the lower layer having the less velocity, so as the Newton's third law, it is also trying to drag in this opposite direction. It is creating some force in this direction. It is creating the same and opposite force in this opposite direction. And it will shape in this way. So it will shape in this way. Velocity will be shaped in this way. So here some different. So it adjusts in this way. So opposite force. This force is nothing but the shear force. So shear force is coming in this way into the picture. This top layer, the top layer, is trying to drag the bottom layer. And bottom layer, because of the lower inertia, more inertia, it is not allowing the top layer to go further. So that is adjusting in this way. So that's why until here the velocity is u, here the velocity is u. And some force is acting because of its, this force per unit area will gives you the stress. So one layer to other layer, the shear stress is acting because of the velocity difference. Because of the velocity difference. As the top layer having more velocity, it tries to drag the bottom layer. And similarly, the bottom layer having less velocity, it is given the reaction forces according to the Newton's third in opposite direction. And this force per unit area, it gives you the shear stress. That is the concept in here. So now here, the velocity diagram, whenever we are drawing it, so what you see here, the velocity is 0. The top, if you one by one layer, if you go along this way, so two position is, let you take it is a along x direction, it is along y direction. So at x is equal to some values. X is equal to 1 meter you are checking, x is equal to 2 meter you are checking. What is the velocity? The velocity profile. So here, the velocity profile, if you see, so at the above layer, there is the velocity higher, further higher, and here it will get 99% of initial velocity. So here is the velocity profile at here. Here, what is happening? At the plate, nearby to the plate, it is 0. Top layer is the top, just above the adjacent layer, its velocity. Now you take here the velocity and here velocity, which is more? Of course, the previous portion, there is a more velocity. Because as you go along the x direction, the more and more number of collision will be takes place, and it tries to retard the motion. So that is why in here, the same location, here, let you take the same y location. Previously, the velocity was more. Now, if you see here, the velocity is less. Further, if you go this way. So the velocity profile will be like this right here. So in this way, it is varying. So here, after going a certain distance, it is getting the, after going a certain distance, it is getting the 99% of the previous more distance. Here, less y, you are getting the 99% of previous velocity. Here, the y value is more. If you go further x distance, if you see, this will be further reduced. If you check here one more, the same way it will be reduced further. First, because as you go along x direction, more and more number of molecules is colliding with each other. Infinite number of collision will be taking place. So it is getting, the velocity is getting retarding continuously. So here also it will be like this. So at this location might have putting the 99% of the previous velocity. Okay. Now the concept of the rate of angular deformation of shear strain rate we'll see. So as you give here some shear stress, as the shear stress is acting over here. You see one layer to other layer, we have already told you that if that is the layer, and just next layer, due to the velocity difference, this layer having velocity u, this layer having velocity u plus delta u. So due to this, some force is acting, and force per unit area comes as a shear stress. And due to the shear stress, the continuously fluid medium is deformed. At t is equal to 1, it was here. So previously, this element, these two sides were perpendicular at t is equal to 0. At t is equal to 1, it creates some angle. Further, t is equal to 2, some further more angle. So continuously angular change is occurring. This is called the angular deformation. So angular deformation is taking place with the time. So that's why the concept is coming, rate of angular deformation. Because we are interested to know about the rate, because it is depends on the time. So per unit time, how much angle changes is occurring. That is another name is the shear strain rate. So per unit time, if the angle change is delta theta is occurring at the time delta t time, if the angle change is delta theta, so unit time how much? Delta theta by delta. This can be written as the theta dot, or known as the rate of angular deformation. Rate of angular deformation. So let you see here the delta theta here. And delta theta here as it is occurring. Just we'll see that topic in the next portion. Just 1 minute. Here, if you see the layer, first layer, bottom layer, it is a top layer. So bottom layer having some velocity initially, it is take some velocity. Here the velocity is more. How much the velocity is more? Delta U. Whatever the velocity, here the velocity, let you take U, here U plus delta. This layer. The first layer is the second layer. Two layers we are considering. So due to the velocity, the angle change is occurring at some time, at delta t time. So this portion, that you take the A name. So this portion after delta t time, it comes at here, A dash. So what is the A dash? How much it is shifted? It is shifted like the U plus delta U. Net displacement. Some displacement is occurring. Previously it was at here. Previously it was at here A. Now it is at here. Previously A and B was like that. Now it is a B dash. So A dash is and B dash how much? U delta T. That is the displacement. So if you draw a perpendicular line like this way, so what is this values? What is this one? Because B dash U delta T, so this also U delta T. So remaining part is delta U delta T. This part. And what is the distance between two layers? Delta Y. Delta Y is the distance between two layers. So tan delta theta, if you take the tan delta theta, so it will gives you delta U delta T divided by delta. Now this theta values, if it is very small, so tan delta theta, you can write it down, delta theta. If the theta value is small amount, so delta theta is equal to delta U delta T. So delta theta by delta T, rate of change of angular deformation, rate of angular deformation is equal to U by E. Now the limiting condition we are taking, limit. What is the limit? Delta T tends to 0, here limit delta Y tends to 0. Very in between two very small amount you are considering. So what is coming? Theta dot limiting values du by dy. That is nothing but a It looks like a velocity gradient, but better to say the strain rate. Strain rate. So it is like a velocity gradient. Some velocity by according to the y direction. So along the y direction, what is the velocity changes? So this is the concept of the rate of deformation. So theta dot is equal to du by dy. So it looks like a velocity gradient, but better to say it is nothing but a shear strain rate or rate of angular deformation. So that is the concept here. Now, what does the Newton says? So Newton says here that the shear stress is the reason of this theta dot. Shear stress and shear strain rate having some relation, and this relation is the proportional relation. That is comes from the Newton's law of viscosity, single law. It is a shear stress is linearly proportionate with the strain rate of shear strain. Shear strain rate, you can say it like this. So it is nothing but a constitutive behavior. It's nothing but a constitutive behavior. So constitutive behavior means Hooke's law you have seen. If you remember Hooke's law, the stress is proportionate to the strain. We are talking about the Hooke's law, we have seen it. The Hooke's law in strength of material. So from here we can derive this is one proportionate constant that is nothing but a material property. What is the name? Elastic modulus. His name was the elastic, Young's elastic, Young modulus, we are telling it, or elastic modulus. Young modulus. The same way, so why it is a constitutive behavior? Constitutive behavior because we are getting some property that is comes from the material. Similar here, the shear strain rate is proportionate to the shear stress, proportionate to the rate of shear stress, shear strain. From here also, the proportionate constant we are getting, that is a material property. This is a material property, mu. And which is nothing but name is the dynamic viscosity. Which is nothing but here name is the dynamic viscosity, mu. So mu is shear stress by strain rate. Shear stress means force per area, shear force per area, and strain rate. So what should be the unit? Force unit, we know the Newton per meter square area. So force per area divided by strain rate. Strain rate means the second inverse. So ultimately the unit of the dynamic viscosity is coming as the Newton second per meter square. Why strain rate second inverse? Because strain rate we see du by dy. So du, what is the meter per second velocity? And it is the meter. So 1 per second inverse. So it can be say in the SI unit Pascal seconds also. The unit of the viscosity Pascal second, the SI unit. For the case of the CGS unit, if you're talking about the CGS unit, so just replace Newton by dyne. Second is the same and centimeter square. dyne second per centimeter square. It's another name is the poise. In the name of engineer, poise. Conversion of the SI unit and the CGS unit. So 1 Newton second per meter square is equal to 1 Newton is the 10 to the 5 dyne. 1 second is the same 1 second divided by 1 meter square. If you convert it to the centimeter square, 10 to the 4 centimeters. So 10 to the 5 by 10 to the 4 only 10. So 1 SI unit is equal to 10th of CGS unit in the dynamic viscosity. This conversion you will see when we are going to the problem, it will giving you as a poise, so you have to convert it to the. So unitary you have to adjust in this way. So better to say 1 Newton second per meter square is equal to 10 poise. It's a very important relation, you can say. So that is the thing we are talking about. Next, we'll see the kinematic viscosity. But before this, another time we have write it in the dynamic viscosity unit. Sometimes it is written as in different manners. Because Newton, we could be able to write kg meter per second square. That is the Newton. Newton we are writing kg meter per second square into second divided by meters. Just to so it will comes in this way kg per meter second. Kg per meter, same thing. SI unit you can write it Pascal second or kg per meter second. Don't be confused with this. That's all. Next we'll see another thing, the kinematic viscosity. But if okay, dimension wise, if you write the dimension of the viscosity, what would be the dimension? So dimension of the dynamic viscosity, if you write, so dimension, the force dimension, m L t to the power minus 2, the force dimension, divided by the area. And that is the tau. And that is 1 by t. Inverse. Strain rate. So m L minus 1, t minus 1. That is the dimension of the dynamic viscosity.